Hello, everyone. Welcome to our talk. This is Le Wu from Baidu Security. In this talk, I will talk about our research about the Android Ion driver. We found a series of vulnerabilities in an Android Ion driver, and they're just like hidden mines in Ion. And we named the series of vulnerability Explosion. In this talk, we will dive into Explosion. The research is finished by me and my colleagues, Xuen Li and Tim Xia. And here are some introductions about us. I am interested in Android Linux bug hunting and exploit. I found over 200 vulnerabilities in the last 2 years, and I am top 1 in Android chipset security program and MediaTek mobile security program. Xuen Li is interested in Android and Linux kernel bug hunting, and he's the author of One-Click Root Master and so on. Tim Xia is a staff security researcher at Baidu, and he's also a previous PACSEC and HITB speaker. Let's get started. Here is the agenda of our talk. First of all, I will introduce Ion about what it is used for and why we research about it. Second, I will show some basic use of Ion, and then I will dive into the explosion and talk about how we found those vulnerabilities. After that, I will make some reflections on explosion. At last, I will discuss the future work. So let's have a look at what is Ion. Ion is a generalized memory pool manager introduced by Google to address the issue of fragmented memory management interfaces across different Android devices. At the very beginning, there are many drivers in Android doing the similar memory allocation work. For example, some of them are used to allocate physically contiguous memory buffers, where others are used to allocate non-contiguous memory buffers. Google noticed these fragmented memory allocation components and introduced Ion. Ion centralized all kinds of memory allocation needs. In Ion, there are many different memory pools. Each memory pool is called Ion heap, and every Ion heap can be used to allocate a specific kind of memory buffer. For example, the Ion heap system is used to allocate memory buffer based on the vmalloc. And also, vendors can use Ion interfaces to add their own custom Ion heap to allocate any special memory buffer they need. Except for the functionality of Ion, there are some other features of Ion that interest us a lot. First, Ion is a common Android driver, so any vulnerability in it can affect many Android devices. Although Ion started to be replaced with DMA buff in Android 12, millions of devices still use Ion, and it will survive for a long time due to the fragmentation of Android. Second, the Ion device can be accessed by untrusted apps, making it a perfect exploitation target, just like the binder device. Third, as I mentioned, Ion is a memory management component. Vulnerabilities in memory management components are proven to be dangerous, such as the dirty cow. At last, Ion went over multiple refactors from upstream. Around 2012, the first version of Ion, known as Legacy Ion, was introduced. And in 2017, the first refactor to Ion happened. After that, in 2019, the second refactor to Ion happened. In 2021, Ion started to be replaced with DMA buff heaps in Android 12. So we started to think about why there are multiple refactors and why Ion ends up with a removal in Android kernels. Maybe there are some insecurity issues in it. After a long time of bug hunting, we have found over 40 vulnerabilities in Ion, which we named Explosion. and millions of devices are affected. Before diving into ExplosION, let's have a look at the use of legacy ion. This can help us understand the vulnerabilities in ExplosION later. And because the legacy ion is the first version of ion, it shows us a complete design and implementation of ion. So let's have a look at the use of ion. First of all, we can use ion to allocate memory buffers from user space. And then for a user process, it can open the ion device and then it will get a client FD. After this, we can use the ion alloc command to allocate a memory buffer with Cisco ion control. This operation will trigger ion to create an ion handle object. An ion buffer object will be associated with this ion handle object. And this ion buffer object represents the memory buffer allocated for the user process. The ion handle ID will be copied into the user process. With this ion handle ID, the user process can do further operations to the memory buffer. Also, a user process can free the memory buffer from user space. This can be finished with an ion free command. We only need to pass the ion handle ID to the ion driver, and then all these kernel objects and the memory buffer will be released. And buffer sharing is a really important feature of ion. We can map a memory buffer into both user space and kernel space with ion. To finish that, we can use the ion share command to send a buffer sharing request to ion. And ion will create a dmbuff object to associate with the ion buffer. And the FD of this dmbuff object will be exported to the user space. And then the user process can map the memory buffer into user space by mapping the dmbuff FD. And also, we can use a few APIs to map the memory buffer into kernel space. After these operations, kernel space and user space will share this same memory buffer. And also, the ion driver is a base driver which can be used by kernel drivers. Drivers in kernel space can allocate memory buffers with API ion alloc, and they can also free memory buffers with API ion free. There is also an API ion map kernel to map a memory buffer into kernel space. We need to note that the virtual address of the memory buffer will be cached in the ion buffer object to accelerate the map operation. And API ion unmap kernel is used to unmap the memory buffer from kernel space. So for now, we have known some basic use of ion, and it's time for us to dive into ExplosION. When we decided to do bug hunting in the ion driver, the very first question was where to start and how can we find bugs in ion more efficiently. Of course, we can do the job just like the old days, but what is the best way for us? After we know more and more about ion, we found that ion is very different from those regular drivers. There are a few characteristics of it. So we thought that maybe we should do targeted bug hunting for each characteristic of ion, because we can use some targeted methods to guide our bug hunting, which could be more efficient. And the final result proves that our strategy is correct. So far, we have found 4 characteristics of ion. Each one of them can be a perspective for us to do the targeted bug hunting. The first characteristic is that ion is a base driver used by vendors. The second one is the customization of ion. The third one is vendors' modification to ion. And the last one is the buffer sharing feature of ion. So far, We have found vulnerabilities buried in these 4 characteristics. And all these vulnerabilities formed ExplosION. So in the following sections, I will discuss these 4 characteristics of ION and talk about how we found vulnerabilities in each of them. Some typical vulnerabilities will be detailed too. Here is the architecture of legacy ION. As you can see, the ION driver is here. And there are many interfaces for user space, and the user's process can call these interfaces through syscall like IO control. The first characteristic of ION is that ION is a base driver used by vendor drivers. There are many ION interfaces for kernel space, such as ION alloc, ION free, ION map kernel, and so on. These interfaces can be used by vendor drivers to finish their work. The second characteristic of ION is the customization of ION. ION provides the interface for vendors to add their own custom ION heap. And also, ION provides the interface for vendors to add their custom IO control commands to operate on memory buffers. As a result, there would be many customizations added by vendors to ION. The third characteristic of ION is the vendor's modifications to ION core. ION core is developed and maintained upstream. Usually, vendors just use the interfaces of ION core to do their work. But actually, we found that many vendors would modify ION core for some purpose, such as debugging. The last characteristic is the buffer sharing feature of ION. A memory buffer can be mapped into kernel space and user space at the same time. This could be a really interesting feature because several kinds of vulnerabilities have been found in such features. After the overview of these 4 characteristics, let's get into each of them. And I will disclose some bug hunting methods and some vulnerabilities related to each characteristic. First of all, we know that ION is a base driver used by vendor drivers. There are many ION core interfaces provided for the kernel. And we found that ION core interfaces are widely used in the vendor drivers, including camera drivers, video drivers, and many other vendor special drivers. When we try to hunt bugs in this characteristic, there are 2 aspects to be considered. The first aspect is that there could be vulnerabilities in ION core interfaces. This kind of vulnerability could affect all vendor drivers. The second aspect is that vendor drivers might misuse ION core interfaces, resulting in some vulnerabilities. So according to these aspects, we analyzed the design and implementation of all ION core APIs for kernel space and their correct usage for vendor drivers. We also checked the code of many vendor drivers to see if they use the APIs correctly. And we finally found some typical vulnerabilities. There are 2 vulnerabilities from ION core, which are CVE 2021 0929 and CVE 2021 39714. There is a vulnerability caused by vendor drivers' misuse of ION core APIs, which is CVE 2022 20110. Let's have a look at the CVE 2021 0929 and CVE 2022 20110. CVE 2021 0929 will affect ION version 1, 2, and 3. The root cause of it is that ION core exposed an API to user space, which it shouldn't be. A use after free issue would be introduced into vendor drivers by ION core in a specific use scenario. Here is an ION use scenario that can be seen in many vendor drivers. In the user space, it can create a DMA buff FD with ION, and this DMA buff FD will be passed to the vendor driver through the syscalls like IO control, and then the vendor driver will create an IO handle object by importing the DMA buff FD. After that, the function IO map kernel will be called to map the memory buffer represented by the IO handle into kernel space. The kernel virtual address will be returned from function IO map kernel. The vendor driver would reference the kernel virtual address to do some work like writing data into the virtual address. This use scenario is simple, but when we started looking into the interfaces provided by the DMA buff FD, we found something interesting. There is a command in the IO control of DMA buff FD, which is a sync command used to do memory sync operations. But we found that with this command, we can unmap the kernel virtual address mapped by the function IO map kernel. As you can see here, the virtual address gets unmapped in the kernel space. As a result, a use after free would happen in a risk condition like this. We can manage to unmap the kernel virtual address right before the vendor driver is going to reference it. This will definitely cause the use after free. The most interesting point of this vulnerability is that you cannot trigger it in ION core. It can only be triggered in the specific use scenario of vendor drivers. This makes it a really typical vulnerability introduced by ION core, but affects vendor drivers. CVE 2021-22-20110 is a vulnerability affecting a vendor's devices with ION version 1. The root cause of it is the misuse of ION core API by a vendor driver. A use after free will happen by triggering the issue. As we know that ION map kernel is used to map the memory buffer into kernel space. The kernel virtual address will be cached in the v_addr field of the ION buffer object. There is also a reference count field, kmap count for the v_addr field. We can see that during the map operation in this function, both v_addr and kmap count are protected by two mutex locks. This can prevent issues from happening in a risk condition. The v_addr of ION buffer is an internal data of ION. So if vendor drivers want to get the virtual address of a memory buffer, they should call the function ION map kernel instead of accessing v_addr field of ION buffer directly, because that would cause the UAF in a risk condition. In a driver of vendor A, we found that it's accessing the v_addr and kmap count field of ION buffer object directly without taking the mutex locks. This would cause a use after free in a risk condition like this. As you can see, in thread A, right after it has gotten the kernel virtual address from the v_addr of ION buffer, this kernel virtual address can be unmapped in thread B with the function ION map kernel. And then when thread A references the kernel virtual address, the UAF would happen. This vulnerability is a typical one caused by vendor drivers' misuse of ION core API. Let's have a look at the customization of ION. ION provides several interfaces for vendors to do customizations. So we were wondering, could there be some security issues in the customization code? Vendors can use the function ION device add heap to add their custom ION heap. Every ion heap must implement its ion heap operations. Ion heap operations contains the functions used for memory allocation, free and map operations, and so on. Vendors need to implement these functions for their custom ion heap. And also, vendors can add custom IO control commands for their own buffer operations. We found that most vendors would add their own custom IO heaps, and most vendors would add custom IO control commands, such as vendor A and vendor B. As you can see, these two vendors add their own IO control commands. In Android ecosystem, the customization is proven to be more vulnerable. So there might be vulnerabilities in the customizations of ION. So after a long time of bug hunting in the customizations of ION, we found dozens of vulnerabilities. Many of them can be used to do privilege escalation. All the vulnerabilities in this page had already been fixed by vendors. Vendors' modification to ION core is an important characteristic of ION. We know that ION core is maintained upstream and vendors should not modify the ION core. But the truth is that some vendors are doing modifications to ION core. For example, we found that vendor A adds some commands into the original function ION control, and vendor B adds some debug code into the original interface ION alloc. All these modifications might introduce issues. There are two aspects we need to pay attention to. The first aspect is that vulnerable modifications can introduce new vulnerabilities into ION core. The second aspect is that code merge conflicts can happen due to the modifications. The missing patch might cause the no vulnerabilities not fixed, and the wrong patch might introduce some new vulnerabilities. According to the assumption, we analyzed the modifications made by many vendors. And also, we investigated dozens of known issues of ION and checked if they are fixed well in the downstream up vendors. And it turned out that our assumption was correct, and we found a few vulnerabilities. There is a vulnerability introduced by a vendor due to the vulnerable modifications, which is CV 2021-0422. And there are two vulnerabilities due to the missing patch and two vulnerabilities due to the wrong patch. Let's have a look at the CV 2021-39801 to understand how the vulnerabilities get introduced because of the missing patch. This vulnerability affects a vendor's devices with ION version 1. The root cause of it is that the patch of a known issue is missing, and this results in a use after free issue. Let's have a look at this known issue. It happens at the ION free ION control command. As we already know, with the ION free command, we can manage to release an ION handle object. But with this word of ION free, if we try to call ION free command in user space continuously, we will release the ION handle object no matter how many times it has been referenced by others. To be more specific, the ION handle object in kernel space can be released at any time from user space. As a result, a use after free issue would happen in many places where the ION handle object gets used. For example, the use after free issue would happen in the ION alloc command, like you can see. What else? Quite a few UAF would happen in vendors' customizations if the ION handle gets used there. Actually, the issue has been assigned CVE ID in 2017. Here is the patch for it. But the fact is, although 5 years have passed away, the patch for this vulnerability has not been applied in many Android kernel branches, including some Android common kernel branches, upstream kernel branches, and also some vendors kernel branches. This issue is a typical one due to the missing patch. Let's see the last characteristic of ION, which is the buffer sharing feature of ION. Actually, the buffer sharing feature of ION is a really attractive characteristic that has been researched by several security teams. For example, there is a paper, Android ION Hazard, and 2 kinds of vulnerabilities introduced by ION buffer sharing are revealed in this paper. And also in another blog written by the researcher from Google Project Zero, the double fetch vulnerability introduced by buffer sharing of ION is revealed. And the double fetch is like this. In kernel space, the memory buffer will be fetched twice. The first fetch is for the checking operation to make sure the data in the memory buffer is valid. And for the second fetch, the data in the memory buffer will be used. But because the memory buffer is shared between user space and kernel space, the user process can do some malicious updates to the memory buffer. And this will make the checks in the first fetch invalid. And issues might happen when kernel uses the data in the memory buffer. According to the pattern of the double fetch issue, we found 3 more double fetch issues in a vendor's APU driver. And here is a question we can think about. Is ION the only component that has the buffer sharing feature? Maybe we can find more double fetch issues in the buffer sharing feature of other components, such as the DMA buff subsystem. After all these discussions about characteristics and the vulnerability buried in each of them, it's time for us to see what we can do with ExplosION. We succeed in getting root of Android devices with 1 vulnerability in ExplosION. And we bypassed the KASLR and disabled the SLinux. This can be finished from any untrusted app with no additional privilege needed. And actually, there are a few other vulnerabilities in ExplosION we can also use to finish privilege escalation. And the exploit video is here if you want to see. Let's make some reflections on ExplosION. We already knew that ION has went over quite a few refactors from upstream. So in some way, ION keeps improving in many aspects. And the first version of ION, which is legacy ION, has been used since around 2012. And now many Android devices are still using it. There are many bug fixes and optimizations from time to time. And then in 2017, ION gets refactored. ION clients and handles are removed. Some IO control commands are removed too. This makes ION more brief, which brings more security. In 2019, in order to adapt ION to generic kernel image, ION Android common kernel version 5.4 introduced a framework for modularizing vendor custom ION heaps while keeping the ION core built in. To be more specific, the ION core becomes a part of the GKI image, and vendors cannot do any modification to ION core anymore. So this will definitely get rid of vulnerabilities caused by the missing patch, the wrong patch, or vulnerable modifications from vendors. After 2 years, ION started to get replaced with DMA buff heaps in some devices of Android 12. According to the official statements from Google, DMA buff heaps have some advantages in security, ABI stability, and standardization. However, we have noticed that millions of devices are still using Android version 11, 10, or even older Android versions. Lots of work still needs to be done by vendors to make sure ION is not attacked. So here are some suggestions for vendors. First, vendors should apply the refactors as soon as possible. We make this suggestion for a reason. As mentioned, ION has been refactored upstream since Linux kernel 4.12, which makes ION more brief, but we noticed that some vendors didn't apply this refactor even in their 4.14 kernels. This can be dangerous because the older version may not be maintained well by the upstream community. Second, vendors should apply the patch quickly and carefully. Sometimes patching a vulnerability is not that simple, especially when some code has been modified by vendors. Code merging conflicts can happen. Third, vendors must understand the ION APIs well. This can help vendors get rid of some API use issues. At last, vendors should be careful when they do customizations to ION because the customization is always attractive for bug hunters. It's time for us to discuss the future work. We know that ION has been replaced with DMA buff heaps in some devices of Android 12. So are the DMA buff heaps secure? We found that DMA buff is very similar to ION. First of all, DMA buff component is also a base driver used by kernel drivers. This is just like ION. There are also customization interfaces in DMA buff. Vendors can use these interfaces to do their customizations. And buffer sharing is also a feature of DMA buff. Our next step is to use the bug hunting methods we used in ION to do some more research on the DMA buff component to see if there are issues in it. Thanks to Chen Fubao, Mo Yinfan, Shu Fanyang, Lin Wu, and Haikuo for helping me with my slides, and they just made great suggestions. And by the way, because of the limited time, I have put the details of other ION vulnerabilities we have found in the supplement part of the slides. You can read them if you are interested. And now I will take questions from the audience.